To manufacture modern integrated circuits, silicon wafers must survive a gauntlet of up to 1,200 unique processing stations. It is arguably the most complex manufacturing environment on Earth. These facilities operate on the flexible job shop principle. At any given moment, a single factory might juggle 1,500 different products. Each product follows a specific recipe, moving through lithography, doping, and etching, often looping back through the exact same machines multiple times. Finding the most efficient path for every product through this maze is a mathematical constraint known as an NP-hard problem. Trying to calculate a perfect schedule for thousands of lots moving across hundreds of machines, the possible permutations rapidly explode into the billions. Even if a computer could finalize that master schedule, it wouldn't survive contact with reality. A single machine going offline for maintenance, or a slight delay in a chemical process, instantly invalidates the entire static plan. Traditional centralized computing relies on linear optimization. It gathers all factory data, processes it in a central brain, and pushes out a schedule. In a highly dynamic environment, it simply takes too much time to recalculate the math every time a physical variable changes. To keep these multi-billion-dollar facilities operating efficiently, engineers are forced to abandon the concept of a deterministic top-down master brain entirely. The alternative is swarm intelligence. In biological systems, vast populations coordinate complex maneuvers and solve logistical problems without a central leader or a master blueprint. Instead of a single computer attempting to govern the entire factory, control is distributed. The factory is broken down into autonomous agents, the individual machines and the products themselves, which operate using strictly defined mathematical local rules. By following these localized rules, the collective group naturally self-organizes. When constraints shift, say a pathway is blocked, the individual agents react to their immediate neighbors and automatically adjust, maintaining systemic flow. To determine if this biological principle can manage an NP-hard factory, researchers run digital twin simulations. They test whether algorithms based on the foraging behavior of ants or the diffusion of human hormones can successfully schedule the production floor. Because engineers cannot risk a live production run on unproven protocols, they use simulation frameworks like SwarmFabSim. This creates a digital twin of the factory, providing a safe environment to test stochastic swarm-based rules. Inside the simulation, the factory is populated by interacting agents. Work centers represent clusters of related equipment. Machines are the individual processing nodes, and lots, the standard 25 wafer carriers known as FAUPs, act as the mobile agents navigating the network. The swarm's task is to optimize two targets. They must minimize makespan, the total time it takes a lot to finish its complete recipe, and reduce tardiness, measuring how long a product sits idle waiting for an available machine. The most severe threat to these metrics is the formation of WIP, or work-in-progress waves. These occur when production shifts from batch-oriented machines, which process many lots simultaneously, to single-wafer machines. Groups of lots exit the batch step at once and crash into the queue of the next machine. A successful swarm intelligence algorithm must empower the local agents to autonomously detect and smooth out these WIP waves before they disrupt the entire floor. The first contender in the simulation is ant colony optimization, a framework driven by the biological concept of Stigmergy. Stigmergy is a method of indirect communication where individuals coordinate by modifying their shared environment. In nature, ants achieve this by depositing volatile chemical trails as they forage. In the digital twin, the lot agents act as the ants. When a lot finishes a process, it measures the time it spent waiting and working and deposits a digital pheromone on that specific machine. Machines that process lots quickly accumulate stronger pheromones, reinforcing faster routes over time. This equation dictates the swarm's behavior. When a lot reaches a fork in its recipe, it doesn't await central instructions. It calculates its exact routing probability using this formula. The decision relies on two competing weights. Tau represents the historical pheromone strength, indicating how fast a machine has been. Eta represents the current heuristic information, essentially how short the machine's queue is right now. The alpha parameter acts as a tuning variable. Adjusting alpha allows engineers to mathematically tune the balance between exploring new machine routes based on immediate queue length versus exploiting the historically proven fast routes marked by heavy pheromones. By executing this math at every node, ant colony optimization replaces static schedules with a decentralized routing protocol, adjusting based on the system's collective history. The competing model abandons insects entirely, drawing inspiration instead from the human endocrine system, the artificial hormone algorithm. The operational mechanics here diverge sharply. While ants lay historical trails to signal where they have been, hormones broadcast an urgent state of present need. This equation illustrates the core trigger. Factory machines act as glands. When a machine's queue begins to empty, it mathematically produces an artificial hormone. The fewer lots waiting in its queue, represented by Q, the higher the volume of hormone the machine secretes. This signal utilizes a mechanic called upstream diffusion. The hormone flows backward through the factory's network, traveling in reverse along the established product recipes to reach the preceding workstations. The lot agents respond to these signals. If a lot detects a high concentration of hormone matching its next required step, it experiences a mathematical attraction. Instead of choosing a physical route, the lots use this attraction to reorder their priority within their current queue. This local rule allows the swarm to naturally prioritize time-coupled lots, pushing them towards starving equipment before that machinery can register idle time. Hormones create a predictive, self-reinforcing pull system. They anticipate starvation and bypass sequential processing through the constant diffusion of local urgency. When researchers ran these biological architectures through 30 simulations in SwarmFabSim, the output data revealed a massive divergence in efficacy. This data table compares both swarm algorithms against a baseline across flow factor, tardiness, and uptime. The hormone algorithm outperformed the baseline and ant-based rules, showing consistent improvements across every scenario. However, the ant algorithm failed, performing slightly worse than simple baseline rules. Mimicking nature is insufficient. The specific mathematical architecture of a local rule strictly dictates whether a complex system will thrive or degrade under pressure. Why did ant colony optimization, a protocol with a proven history in logistics, fail inside the semiconductor fab? The deciding variable is the information horizon. The simulated ants were mathematically constrained, evaluating pheromones only for the immediate next work center. They couldn't sense bottlenecks forming further down the line. Conversely, hormones used upstream diffusion to gain a multi-step network view, coordinating actions across distant stations simultaneously to prevent future starvation. This superior multi-step vision comes at a strict computational cost, requiring exponentially more computing time to simulate than the localized, immediate rules of the ants. Expanding the information horizon allows factories to escape centralized control, creating a self-organizing system that adapts to changing production demands in real time.